In the deepest pockets of the world's deserts, the ground offers absolutely nothing. For the communities living here, survival is a daily, grueling physical calculation of how far you can walk before the heat breaks you. In parts of Morocco and Chile, local women have historically spent up to 5 hours every single day navigating steep, rocky terrain, expending massive amounts of energy simply to carry home a few heavy pots of contaminated water. But the cruelest irony of these arid landscapes is that millions of liters of pristine, fresh water are constantly flowing right above their heads. Dense, heavy fog banks, borne over the ocean, regularly sweep across these high-altitude mountain peaks. It is a massive floating reservoir. The moisture is right there, hanging in the air, while the ground below remains completely parched. Bridging that physical gap between the sky and the sand is the ultimate test of human engineering. In the late 20th century, engineers in the Chilean Andes tried to tap into this airborne reservoir. Their solution was brute force. Erect massive, rigid walls of flat plastic mesh on the mountainsides to physically block and catch the fog. This model reveals the flaw. A solid vertical plane in 100-kilometer-per-hour winds isn't catching water, it's a massive sail. When storms hit, the intense pressure overwhelmed the structure. Steel supports buckled, cables snapped, and the mesh tore to shreds in minutes. That single spectacular collapse sent a chill through the scientific community. Global investors pulled their funding, and the idea of large-scale fog harvesting was officially dismissed as an expensive fantasy. The rigid nets failed because they treated the wind as an adversary. Whenever you try to meet extreme weather with inflexible resistance, the weather wins. Years later, an industrial designer named Peter Trautwein reviewed the wreckage in Chile. He realized that to survive hurricane-force winds, the structure couldn't fight the air. He needed to look at how nature solved the exact same problem. His blueprint was the Garoi tree of the Canary Islands. For centuries, this tree kept indigenous tribes alive in a region with almost zero rainfall. This cross-section shows the tree's underlying mechanics. Instead of a flat wall, its canopy is a deep, three-dimensional network. High-speed winds flow harmlessly right through the gaps, while leaves strip moisture droplets from the air. Trautwein's engineering team translated this biological mechanism into a technology called the cloud fisher. They wove a three-dimensional, flexible polymer matrix that mimics the deep branching of the Garoi tree, allowing violent storms to pass directly through. By embracing permeability, the massive nets survived the storms. They pulled millions of liters of water straight out of the brutal Saharan winds without breaking. But catching the water created a severe logistical problem. The harvesting nets sit on an isolated peak in Morocco, 500 meters above the villages that need the liquid, with zero electricity available for pumps. The only way down was immense physical labor. Workers spent months in 40-degree heat, swinging pickaxes to break solid rock by hand, slowly laying 10 kilometers of subterranean piping to let gravity carry the water. This precise method of zero-energy water transport was mapped out 1,000 years earlier. In the year 1001 AD, the pre-Inca Chiribaya culture faced the exact same altitude problem in the Andes. The Chiribaya hand-carved extensive stone channels into steep mountain passes. They trapped airborne moisture using dense tree canopies and channeled the harvested fog water all the way down to irrigate the desert below. Whether it's a modern polymer pipeline in Morocco or a millennium-old stone terrace in Peru, making this system work requires massive human effort and reliance on the raw laws of gravity. Just as the pipeline stabilized, the Sahara delivered a brutal stress test. Satellite radars tracked a massive sandstorm moving directly toward the cloud fisher installations. This creates a fatal mechanical threat. If heavy airborne dust hits fog, it turns into liquid mud. The desert heat then bakes it into a solid crust, completely suffocating the water-catching mesh. To engineer a defense against the mud, the team looked to the driest place on Earth, the Atacama Desert in Chile, and studied the native cactus. This macro diagram highlights the plant's passive self-cleaning physics. The surface of each cactus spine is covered in microscopic, ultra-smooth cones. Dust can't stick to them. When morning dew condenses, drops slide down and wash dirt away. The engineers applied an ultra-smooth coating to their polymer threads, replicating the cactus geometry. Now, the cloudfisher uses the first 15 minutes of a foggy morning as a natural windshield wiper to flush out the mud. Integrating that biological self-cleaning mechanism was the final step. The expensive infrastructure became entirely autonomous, capable of withstanding extreme storms, cleaning itself, and delivering pure water without human intervention. The completion of the gravity pipeline directly shifted the local power dynamic. Management of the autonomous network was handed over to the local Berber women, who now monitor pipe pressure and check for leaks using sensors connected to their smartphones. By eliminating the brutal 5-hour daily trek across the rocks, these women reclaimed 95% of their lost time, allowing them to cultivate fresh vegetable gardens right outside their homes. In 2016, the Moroccan project received the Momentum for Change Award at the UN Climate Conference, securing the technology's validation on a global stage. But the environment is already shifting. As global temperatures rise, coastal fogs are thinning out, and water droplets are shrinking. In response, engineers are actively iterating denser, multi-layered meshes designed to capture this increasingly rare vapor. The success of the cloudfisher proves that sustainable engineering relies on studying the plants that thrive in the dust, learning from the ancient civilizations that pulled water from the sky, and using modern science to weave those survival strategies together.